So let us recall what we have did in the previous lecture. In the previous lecture, we have discussed what is a Rogers formula for Legendre polynomial, and we have derived that it is polynomial, Legendre's polynomial Pn of x is expressed as 1 upon 2 power n into n factorial into nth derivative of x square minus 1 raised to n. Also, we have discussed the orthogonal property of Legendre polynomials, which is described as integration from minus 1 to 1 Pn of x dx. Pn of x into Pm of x dx is 0 if n is not equal to, if equal to, not equal to m, and it will be 2 upon 2n plus 1 if it is equal. So this is the orthogonal property and Rogers formula we have discussed in the previous lecture. In this lecture also we are discussing certain examples based on Legendre polynomials. So let us have this example. Find the value of P0 of x, P1 of x, P2 of x, P3 of x, and P4 of x. So the question is to calculate what will be the value of this Legendre polynomials. We know that now the Rogers formula, it is Pn of x is equal to 1 upon 2 power n into n factorial nth derivative of x square minus 1 raised to n. Now for n equal to 0, we have P of 0, which is 1 upon 2 power 0 into 0 factorial. So I have to substitute n equal to 0 into this expression. This is the 0th derivative of x square minus 1 power 0, which is x square minus 1 raised to 0. So all the things will gives you 1 because 2 power 0 is 1, 0 factorial is 1, and this is also 1. So P0 is 1. For n equal to 1, we'll have P1 of x, which is 2 power 1 factorial d by dx of x square minus 1 power 1. So when you differentiate this quantity, we'll have it as 2x. So P of x is x, P1 of x is x, that we got. For n equal to 2, that is P2 of x, which is as per the formula 2 power 2 factorial b square y by dx square x square minus 1 square. Now let us take the first derivative of this. This will gives you 2 raised to 2, so it is 4 into 2 d by dx of 2 into x square minus 1 into 2x, because the derivative of x square minus 1 whole square is 2 times x square minus 1, and the derivative of x square is 2x. If you multiply this inside, this is d by dx of 2 into 2 is 4, so that I can take out. This is x cube minus x will have. So this will gives you 1 by 2, 3x square minus 1. So that is your P2 of x. Now for n equal to 3, into this formula. That is P3 of x is 1 by 3, 2 power 3 into 3 factorial d cube by dx square, sorry, x cube, x square minus 1 whole cube. Hence, this will give you 2 raised to 3, 3 factorial d square by dx square of 3 into x square minus 1 whole square. The derivative of x square minus 1 raised to 3 is 3 x square minus 1 whole square. And the derivative of x square minus 1 is 2x. And if you simplify this bracket quantity, making a square and doing the derivative, or you can just apply the product rule, whatever you like to do that there. So we'll have, this is 1 by 8 into 6, because 2 raised to 3 is 8, 3 factorial is 6, this 3 and this 2 is common out, and we can write down that here, that is d square by dx square. If you simplify the previous quantity, this is x into x square minus 1 whole square. Again, we'll do the derivative. So this is d by dx of, apply the product rule, x as it is, differentiation of x square minus 1 whole square, that is 2 times x square minus 1 into 2x plus x square minus 1 whole square as it is, a derivative of x is 1. So we'll have this. Further, I can simplify this. This is d by dx of, you multiply this, 2 into 2 is a 4, x square into x square, that is x power 4 minus 4x square plus x square minus 1 whole square. Again, if you differentiate this quantity, this will give you 16 x cube minus 8 x square plus 2 times x square minus 1 into 2x. This is 2 2s are 4, 8 is here, 4 is, so 4 is common out. So that will give you 1 by 2, and this will give you 8x cube minus, not 8, 4x cube minus 2x square. This 4 will be cancel out, and this x square I multiply inside, that is x cube minus x. Hence, the final answer you will have, it is 5x cube minus 2x square minus x. So this is your P3 of x. Similarly, I may give you as an exercise to calculate. This is a homework that you can do it yourself for P4 of x. Now from this, what we get, 1 equal to P0 of x is equal to P1 of x. So let me write that. We can write as a note. So remark. And this one we'll use to express any polynomial in terms of Legendre polynomial. From above example, we get 1 is equal to P0 of x. P0, that is this. 1 equal to P0 of x. X is equal to P1 of x. Then I want what will be the value of x square. So the value of x square from this, what we get is 2 into P2 of x plus 1 upon 3. That is equal to x square, because this is P2 of x. And if you simplify this, this will give you this. But what is 1? 1 I can write down as P0 of x. So first of all, let us write down what is x square. It is 2 times P2 of x plus 1 upon 3. But 1, due to this one, we can write it as P0. So it is 2 into P2 of x plus P0 of x by 3. So ultimately what we can say, this we can express as a polynomial in terms of Legendre polynomial, that is n running from 0 to infinitive an pn of x, where your a0 is 1 by 3. To compare with this one, a1 is 0, a2 is 2 by 3, and rest all of them, that is 3, 4, and so on, all of them are 0. So in general, any of x power k can be expressed as summation n running from 0 to k an pn of x, where ak is non-zero. From this expression, we can, like, for example, for x cube, we can calculate the value of x cube, which is in terms of p0, p1, p2, and so. In similar manner, we can able to write down a polynomial, any polynomial, in terms of Legendre polynomial. So hence, what we can write is, we can write any polynomial p of x equal to b0 plus b1 of x plus b2 of x up to so on, bk x power k, k belongs to n, in terms of Legendre's polynomial Pn of x. So we can able to write down in terms of this. For example, let us take the example and see this. Express 3x square minus 2x plus 5 in terms of Legendre's polynomial. So the question is to calculate this 3x square minus 2x plus 5 in terms of Legendre polynomial. So here we have p of x is this 3x square minus 2x plus 5. Now x square, the value of x square, we can have this 2 times p2 of x plus p0 of x by 3 in terms of Legendre polynomial. So that we can substitute here. So it is 3 into 2 times p2 of x plus p0 of x by 3 minus 2 into x, the value of x is p1 of x. So, and p5 is p0 of x. This 3 will get cancelled out. So finally, if you simplify, this is 2 into P2 of x plus P0 of x minus 2 into P1 of x plus 5 into P0 of x. So if you simplify this will gives you P0 of x will gives you P of x will gives you 6 P0 of x minus 2 times P1 of x plus 2 times P2 of x. So this is 2 times P2 of x, 5 plus 1, 6 times P0 of x. So if you can write down, this is in the form of summation and a running from 0 to 2, an Tn of x, then your a0 is 6, a1 is minus 2, a2 is 2. So I have expressed this polynomial in terms of Legendre polynomial. In similar manner, any polynomial can be expressed in that form. Now let us discuss the next property of Legendre polynomial. Let f of x be an arbitrary function of x on the interval minus 1 to 1. Suppose that it can be expanded in terms of Legendre polynomial. Pn of x as f of x is equal to summation n running from 0 to infinity an Pn of x. Then prove that this an will be n plus 1 by 2 integration from minus 1 to 1 fx Pn of x dx. So this is gives you, if you have, like in the previous example, what we did is the question is to convert this function into the polynomial form of a Legendre, and due to this example or due to this theorem, we can able to find out what is this an directly from this formula. As we have discussed here in the previous, this a0, a1 and a2, using the converting your p0, p1 of x, p2 of x as a function of x, and then you have calculated what is the value of x square from it, and you have substituted that value. Here it tells you you can directly calculate this an value. Let us try to discuss the proof for this result. And one thing here we should note that this series which I have written here, the equation 1 actually, it's called Legendre series because it is in series in terms of Pn of x, Legendre polynomial. So that's why it is known as a Legendre series. Let us discuss the proof of that. This. As per the hypothesis or assumption, by equation 1, f of x is equal to summation n running from 0 to infinity an pn of x dx is there. That means this is a0 p0 of x plus a1 p1 of x plus a2 p2 of x and so on. Now consider, so they have already given you the something here that an you can calculate using this integration. So we consider that integration fx into pn of x dx. The value of fx we substitute here, that is integration from -1 to 1 pn of x a0 p0 of x a2 p2 of x, sorry, a1 p1 of x plus a2 p2 of x up to so on dx. Now what is this? This is by orthogonal property, which we already discussed here. The orthogonal property is this Pn of x into P2 Pm of x, integration from -1 to 1. If they are not equal, then the answer is 0. If they are equal, then the answer is this. So if I use this orthogonal property here, then it is Pn of x into P0 of x, integration is there. So that quantity is 0. So only non-zero quantity will occur when this n, whenever n is here. So this is by -1 to 1 an into Pn of x into Pn of x dx is the only left quantity from this. This is because by orthogonal property of Legendre polynomial. So due to that we have this. Now what is the answer for this? It says that it is 2 by 2n plus 1. So that's why this will gives you, and an is independent of that. So I can take out an and the answer is 2 by 2n plus 1, which is -1 to 1 fx pn of x dx. So therefore an you will have it is 2n plus 1 by 2 -1 to 1 fx pn of x is there. So that is our required formula to calculate the coefficient. And using this formula, now also we can solve this example. So instead of doing this whole thing, you may do this using this an. We can able to solve that. Now we have a next thing, it's a generating function. The function on the left side of this 1 upon square root of 1 minus 2xt plus t square, this function is equal to summation n running from 0 to infinity t power n into pn of x. It's called a generating function of Legendre polynomial. This is called the generating function, and we will assume this result. This result we will assume here. Okay, and this is known as a generating function. Now we will solve some examples here. Verify that First one. Pn of 1 will be 1. Second, Pn of minus x is minus 1 raised to n into Pn of x. Third one, Pn of minus 1 is minus 1 raised to n. Fourth is P2 n at 0 is minus 1 raised to n into 1 into 3 into 2n minus 1 upon 2 raised to n into n factorial. And P2n plus 1 at 0 will be 0. So this exercise we have to do, we have to verify, and there are other lots of exercise that's given into the book. You can just go and check that. So we'll use that generating function to discuss this exercise. So we know that this 1 minus 2t x plus t square raised to 1 by 2, that is the square root of t, is equal to summation n running from 0 to infinity t raised to n into p of pn of x is there. So this is the generating function in there. Now here the question is to calculate pn at 1. So I just substitute the x is equal to 1 in this formula. So we will call it this as equation 1. Put x is equal to 1 in 1. We have 1 minus 2t plus t square raised to minus 1 by 2 plus summation n running from 0 to infinity t power n into pn of 1. Now what is this? This is actually 1 minus t square, 1 minus t whole square and whole raised to minus 1 by 2. That is equal to summation n running from 0 to infinity t power n pn of 1. So this is gives you, this quantity will gives you 1 minus t whole power minus 1, because this is square and raised to 1 by 2 is there. That's why it is whole power minus 1. And on the other side we have the same thing, that is summation n running from 0 to infinity t power n en of 1. Now what is this series of 1 upon 1 minus x, which we have to apply here? The series we know it is 1 plus x square up to so on. If we substitute that one, that is 1 plus x square up to so on, and on this side we can expand this summation, that is p0 of 1 plus p1 of 1 t plus p2 of t into t square up to so on. This is the thing. Now if we compare the coefficient of t power n, sorry, here I should have a t because this is t we have. So it is coefficient of t power n, both sides. We get p0 of 1 will be 1. p1 of 1 is 1. So in general, pn of 1 will be 1. That we got from this. Okay, so that is the first things to ask to prove. Now to prove the second one, in equation 1 we substitute x is equal to minus x. So instead of x we just replace by minus x into this expression, because here we need to have en of minus x, that we need to have. So that thing will do. So now replace x by minus x in equation 1. We obtain that 1 minus 2x into minus minus become plus x into t plus t square raised to minus 1 by 2 is equal to summation n running from 0 to infinity t power n pn of minus x. We call this statement is 2. Now I will replace t by minus t into this, replacing t by minus t in the equation 2. No, in equation 1, we have, so this was the equation 1. Instead of t, we have to replace minus t. So this is minus minus become plus. So it will have 1 plus 2tx plus t square raised to minus 1 by 2 is equal to summation n running from 0 to infinity minus t raised to n into pn of minus x. Sorry, pn of x. If I call this as equation 3, and if you compare this, or yeah, you can compare this side is same, that we can see. So by equating 2 and 3, we obtain that summation of t power n into pn of this is same as summation n running from 0 to infinity minus 1 raised to n into t power n pn of x. Comparing the coefficient of t power n, we get pn of minus x, which is on this side, will be minus 1 raised to n into pn of x equal to minus 1 raised to n into pn of x. So this is the things we got. Now the next thing we have to prove is the third thing, that is pn of minus 1 is minus 1 raised to n. Can somebody prove from this one, this quantity? So here you just replace x is equal to 1 in this. If I put x is equal to 1, this is pn of minus 1. Minus 1 raised to n, pn of 1. Pn of 1 is 1. So this third is obvious from this. So to prove third one, replace or put x is equal to 1 into this star. We get pn of minus 1 is minus 1 raised to n into pn of 1. And pn of 1 we have proved already 1. So this is minus 1 raised to n. So that completes the third also. Now to prove the fourth one. So in the fourth one, what we have to do, we have to calculate what is the even terms and odd terms. And in this recurrence formula, I just substitute x is equal to 0 here, because that value I have asked to calculate p2n at 0. So I substitute here x is equal to 0. Let's see what will happen. So let x is equal to 0 in equation 1, we get 1 plus t square raised to minus 1 by 2 summation n running from 0 to infinity t power n into pn of 0 is there. Now what is the expansion of this? And you just recall that the binomial expansion of 1 plus x raised to p. The binomial expansion of this one is 1 plus px plus p into p minus 1 upon 2 factorial x square p into p minus 1 p minus 2 upon 3 factorial cube and so on. So 1 plus t square raised to minus 1 by 2. According to this, t is equal to t square is equal to x. And instead of p, we have minus 1 by 2. So this is 1 plus minus 1 by 2 into t square plus minus 1 by 2 into minus 1 by 2 minus 1, that is minus 3 by 2 upon 2 factorial t raised to 4. Then it will have minus 1 by 2 minus 1 by 3 minus 5 by 2 upon 3 factorial into t power 6 and so on. So this is the expression of 1 plus t raised to 1 by 2. That can be also further simplified and can be write down as 1 minus 1 by 2 t square. This I can rewrite as minus minus become plus, so it is plus 1 into 3 upon 2 raised to square 2 factorial into t power 4. Then it will have minus sign. 1 into 3 into 5 upon 2 into 2 into 2, which is 2 raised to 8, but I can write down 2 raised to 3, 2 raised to 3 and to 3 factorial into t raised to 6. What will be the next term? Will be definitely plus, because there are 4 terms is there. What is that term? 1 into 3 into 5 into 7 upon 2 raised to 4 into 4 factorial x raised to or t raised to 7 plus so on. So this is the expression of 1 plus t power t square raised to minus 1 by 2. That we can substitute here on this side. So hence this is equal to summation n running from 0 to infinity t power n pn of 0. Now if you compare the coefficient both sides, this is also in powers of t, this is side is also in powers of t. So comparing coefficients of t power 2n both sides, we get what we get. First of all, p0 of 1 we have, p1 of 0, p0 of 0 is 0, p2 of 0, p0 is 1 not 0, this is 1, p2 of 0 due to this is minus 1 by 2. P4 of 0, which we got from this 1 into 3 upon 2 square into 2 factorial. Same way we have p raised to 6, p6, which is minus 1 into 3 into 5 upon 2 raised to 3 into 3 factorial, and so on. There are other things is there. And if you can have the powers of p power n plus 1, then that will give you 2n plus 1 at 0 is 0, because there are no index having the odd term. That is p3, p1, all of them are 0. And you can write down this p2, p4, p6 into in general term, that is pn at 0. Since it is an alternating sign, this is minus 1 raised to n. 1 into 3 up to 2n minus 1 upon 2 raised to 2n minus 2 into 2n minus 2 factorial. Sorry, not 2n minus 2, 2 raised to n, sorry. 2 raised to n into n factorial. So both this quantity is we have to prove for this quantity that we have proved that this is equal to minus of this minus 1 raised to n, pn plus 1 is 0. Now lastly, we have also further property of this Legendre polynomials. Let us discuss that. Prove that prove the following. A recurrence relation. First one, n plus 1 into pn plus 1x is equal to 2n plus 1x pn of x minus n into pn minus 1 of x. Now the generating function, we use that same formula for the generating function. So the generating function for Pn of x is 1 minus 2xt plus t square raised to minus 1 by 2 is equal to summation n running from 0 to infinity t power n into Pn of x. We call this as equation 1. This is a generating function. Now we'll differentiate this to get this one. We'll differentiate this with respect to t. What we get? So here we have to differentiate this. So it is minus 1 by 2, 1 minus 2xt plus t square raised to minus 3 by 2. Then inside portion, inside bracket, we have to also differentiate, that is minus 2x plus 2t is equal to on the other side n running from now 1 to infinity, because the first term when n equal to 0 is a constant term. N into t power n minus 1 pn of x is there. So this quantity I may rewrite as, you just observe that this 2 is common out from this 2 and that cancel with this. So this 2 is cancelled. Hence this is written as, and this minus sign if I multiply inside bracket, it will be x minus 1, x minus t, and the rest of the things I can write down this t square raised to 3 minus 3 by 2, so I can write down this is minus 1 by 2 upon 1 minus 2x plus t square raised to 1 is equal to summation n running from 1 to infinity and t power n minus 1 Pn of t is there. Now, if I multiply this quantity and on the other side, so this will gives you therefore x minus t 1 minus 2x t plus t square raised to minus 1 by 2 is equal to 1 minus 2x t plus t square into summation n running from 1 to infinity and t power n minus 1 Pn of t is there. Now, what is the value of this quantity? As per this generating function formula, this quantity is summation of t power n into Pn of t. That we have substitute. We can substitute here. So therefore, this will gives you x minus t into summation n running from 0 to infinity t power n into Pn of x is equal to 1 minus 2xt plus t square summation n running from 1 to infinity and t power n minus 1 Pn of x is there. Now we'll multiply this power t and we'll write down this is as summation n running from 0 to infinity x Pn of x into t power n minus summation n running from 0 to infinity Pn of x t power n plus 1 is equal to, if you multiply this bracket to this one, then it is summation n running from 1 to infinity n t power n minus 1 Pn of x minus 2x, you can write down outside. This t you can multiply inside. That is summation n running from 1 to infinity and t power n Pn of x, and the last term is t square will multiply. So that is n running from 1 to infinity n into t power n plus 1 Pn of x. Now, if you compare the coefficient of power t, if you compare the coefficient here, or t power n, you compare the coefficient of t power n, what we get here, I have to replace, this is n plus 1 is there. So, for that I need to replace, if I want n here, here also I need n, here also I need n. So, I need to replace this n by some another quantity. So, here n plus 1 I am just replacing by n. Here I am replacing n minus 1 to replace n, and here n plus 1 is replaced by n. So this whole quantity I may write down as the first thing is as it is, summation n running from 0 to infinity x Pn of x t power n is as it is. Then it is minus, here n plus 1 is replaced by n. So your n, when n is 0, then it will start with 1. Okay, so now n is starting with 1 here, summation n running from 1 to infinity. You will have Pn, instead of Pn you will have now Pn minus 1x. Due to n plus 1 is replaced by n. So whenever n is there, you have to replace n minus 1. This is t power n. On the other side, that is this n minus 1 replaced by n. So when n is 1, n will be 0. So that is summation n running from 0 to infinity. You will have n. So instead of n, we have n plus 1. So that is n plus 1 Pn of x t power n, that we have. Now p n plus 1, p of n plus 1 is here. Then it is minus 2x is there, summation this quantity as it is, that is n running from 1 to infinity, n into t power n, pn of x, plus summation. Here also n start with n plus 1 is replaced by n. N is starting with n, so it will be start now with 2 to infinity. And you will have n, instead of n we have n plus 1, so it is n minus 1 t power n p n minus 1 x. Now we compare, equating the coefficient of t power n both sides. Here we have x into pn of x. Here we have minus pn minus 1x equal to n plus 1 pn of pn plus 1x. Then it is minus 2n x pn of x plus n minus 1 pn minus 1x. So what will be this? If you simplify this one, if I take this quantity, what we have to prove this quantity? N plus 1, pn plus 1. So that we can write down on the one side. So this quantity on one side, n plus 1, pn plus 1x. This quantity and this quantity, let's take on the other side. So that is equal to, if I take this quantity on the other side and x is common, then it is 2n plus 1x pn of x. And if I take this quantity on the other side, that will be minus n pn minus 1x. This is minus 1. If it goes on the other side, it will be plus 1, and then it will cancel with this. So only the quantity left is this one. So that is the objective we have here to prove. Let us do the next. Second is n pn of x is equal to x pn dash of x minus pn minus 1 dash of x. Here dash represents the derivative of that function. Okay, so that is the things we need to prove here. And I'm giving you, this is an exercise for you. I'm giving you a homework. You may try yourself. Use the generating function to prove, and then differentiate that generating function with respect to x, and then compare the coefficient both sides. That is the idea to do this. Okay, and with this your unit 3 is also finished. If you have any question, you can ask.